Welcome to part B of lecture 1 under module 4. In this lecture, we are going to discuss basics of voltage source inverter and a very simple switching scheme for such kind of inverters known as square wave switching scheme. We shall also discuss some other interesting topic like whether we need body diode for different loading conditions, what is the need for blanking time, and what are the advantages and disadvantages of square wave switching scheme, etc. Now, before we discuss VSI in detail, let us try to understand what type of switches are preferred for voltage source inverter. As we progress along the course, you will see that the switches that are used for voltage source inverter are controlled using pulse width modulation techniques. And as you know, for pulse width modulation technique, we need switches which we can turn on and also we can turn off. That means we need fully controllable switches. An example of such switches are IGBT, MOSFET. In this course, I will be discussing VSI with respect to IGBT mainly. You can apply most of this concept for MOSFET as well, because you know the key difference between IGBT and MOSFET. And before we move further, let us have a quick revision regarding this kind of controllable switches, how they operate. So we'll take a case as shown in this circuit. It is a 10 volt DC source and we have a resistance of 1 ohm and this is a IGBT. Now, if I do not provide any gate pulse to this IGBT, so as you know, this is the gate terminal, this is the collector terminal and this is the emitter terminal. And to turn on this device, we should provide a gate pulse between gate and emitter. So if we do not provide any gate pulse, what will be the current in this circuit? Since we did not provide any gate pulse, so current in this circuit is going to be 0 because this switch is going to be turned off, and also you can see the diode is reverse bias. So current in this circuit is going to be 0. Now what happens if you give gate pulse to this switching devices? Then this switch part will conduct and current will be 10 ampere. It will be plus 10 ampere and it will flow from left to right, this direction. Now let's take a slightly different case where we are connecting our voltage supply in reverse direction. So plus side is on this side and minus side on the top side. Again, we will consider these two cases. What is I when there is no gate pulse provided? So now no gate pulse is provided to this switch, but still you will see that diode will get forward bias and a current equal to minus 10 ampere will flow in the circuit and the direction will be from right to left. That's why I said it is minus 10 ampere. And what will happen if I provide gate pulse to this switch T1? Still you will see current will be minus 10 ampere because this switch is not going to turn on. So from this study, what we can conclude or what we can observe is that for a switch like IGBT to conduct, two conditions must be satisfied. Number 1, gate pulse must be provided, and number 2, it has to be forward bias. And what do you mean by forward bias for the switch? That VCE should be greater than threshold voltage, right? So only when these two conditions are satisfied, we will say that this switch can conduct. This switch cannot conduct in this direction, right? This switch can conduct only in this particular direction. But diode will conduct as soon as it is forward bias. That means as soon as you apply any positive voltage this side and a negative voltage this side, this diode is going to conduct. So conduction of this diode does not depend on gate pulse. So this concept you need to remember when you will be analyzing inverter circuits. And for the voltage source inverter, in this class we will discuss about single phase voltage source inverter. First we will discuss half bridge inverter, whose circuit diagram is shown over here. So as you can see, there are two voltage sources, this VS and VS, and there are two switching devices. So basically you are having only one leg and load is connected like this. And as I discussed, these switches will be mostly either IGBT or MOSFET, You can use some other devices also under special conditions, but in this course we will be mostly using this kind of controlled switches. So with this, if you replace the switch in this ideal switch symbol, so this is an ideal switch symbol. So if you replace IGBT instead of this ideal switch symbol, the circuit will look like this one. And what is the difference between the first circuit and the second circuit is that you can see we are using a single source here, and that midpoint we are creating using two capacitors. So this capacitor will hold half of this total input voltage Vs and Vs. This capacitor will be equal valued capacitor, and this total voltage will be divided in half, and this part will act as a half bridge inverter. Now when you turn on switch S1, so where is S1? This is S1. If I turn on switch S1, so this point B will sit over here and A is at the negative terminal. So this voltage VAB will be minus Vs. And what happens if you turn on S2? Then A is sitting at positive terminal, B will be connected to this negative terminal. So VAB will be directly in parallel to this positive Vs, and hence as you turn on S2, the voltage across load terminal will be plus Vs. Can I turn on S1 and S2 together? No, because if I turn on S1 and S2 together, this DC source will get short circuited through this path. So we should never turn on S1 and S2 together. Now if I turn on S1 and S2 at 50% duty ratio, so basically S1 is turned on for half of the time and S2 is turned on for half of the time. So your output voltage waveform VAB looks like this one. When S2 is on, you are getting positive voltage same as Vs. When S1 is on, you are getting a negative voltage which is minus Vs. Now let's try to see the case for full bridge inverter. So this was the case of half bridge converter. We saw there was only a single leg. In full bridge converter, we will have two legs, leg 1 and leg 2, and we will have total 4 switching devices. And there is a single source. We don't need any midpoint generated by capacitor, or we don't need two separate sources. And as I discussed earlier, this switch will be controlled switches, mostly IGBT or MOSFET. Now, how do you control this kind of converter? And what are the governing rules behind that? So, as I already discussed earlier, you cannot turn on switch in a same leg. So, S1, S4 you cannot turn on together. Similarly, S3 and S2 you cannot turn on together. Because if you turn them on together, they will short circuit this input source. And to avoid their simultaneous conduction, we should apply some dead band or blanking time that I am going to discuss in the next slide. But I can turn on S1 and S3 together and S2 and S4 also, and in some switching strategy we will need that, so that I will discuss next. And this S1 and S2 together and S3 and S4 together, that also we can turn on. So when to turn on which switch, that we are going to study next. Now before that, let me quickly discuss about this dead time which is required to prevent shoot through fault. Now what is shoot through? If you turn on two devices of the same leg simultaneously at the same time, then your DC source is going to be short circuited across this branch, and that is known as shoot through fault. And to prevent that, we should never turn on two switching devices of the same leg. Ideally, these two switching devices should be complementary to each other. And what do you mean by complementary? When one switch is on, for example, let's say this is for S1. So when S1 is on, S4 is off. When S1 is off, S4 is on. And again when S1 is on, S4 is off. So this kind of switching is known as complementary switching. Now this will work good in ideal scenarios. So what you are doing, you are turning off S1 and then you are turning on S4. So you are not turning on them together. So there is no chance of shoot through. But in practical scenarios, what will happen is that any practical devices like IGBT, MOSFET, etc., they will need finite time to turn on and turn off. So even though you are asking the device to turn off at this instant, let's say t equal to 0, it will take some time to completely turn off. Similarly, S4, even though you want it to turn on at t equal to 0, it will take some time to turn on. So you will see there will exist some time where both the devices are conducting, because S1 is not completely turned off, S4 is still turning on. So both of them are actually conducting simultaneously, and that will create a shoot through. So to prevent that, what we should do is, whatever switch you are turning off, then you allow some amount of time before turning on the next device of the same leg. So here we are turning off S1, we are allowing some time, this delta t, and then we are turning on S4. How do you decide this time? You read data sheet of the IGBT or MOSFET that we are going to use, and from that you will get an information roughly how long a device needs to turn on and turn off. So based on that you can decide with some safety margin. So this time is known as dead time or sometime blanking time. Now let us try to understand full bridge inverter in more detail. This is the basic circuit diagram. You have a single DC source and there are 4 switching devices. And you remember what are the rules? You cannot turn on 2 devices of the same leg, but you can turn on the diagonal pairs. You can also turn on either top 2 devices or bottom 2 devices. So if you do that, you end up with total 4 combinations. When you turn on S1 and S2 together, so this point A will be connected to positive side of your power supply. This point B, if you turn on S2, it will connect to the negative part of the power supply. So then VAB will be plus VS. Now if you turn on S1 and S3 together, so where is S1? This one is S1, this one is S3. So if you turn on S1 and S3 together, the voltage appearing across terminal AB will be 0, right? Because it will be the KVL path, and you can see voltage across load will be 0. And if you turn on S3 and S4 together, so B will be sitting at plus potential, A will be sitting as minus potential. So VAB is going to be minus VS. And if you turn on S2 and S4 together, then again VAB is going to be 0. So these 2 switching states where we are getting plus Vs and minus Vs across the load terminal, we call them active states. And these 2 where we are getting 0 across the load terminal, that we are going to call freewheeling stage. Now when you turn on S1 and S2 together, this voltage waveform looks like this. You are getting plus Vs across the load terminal. When you turn on S3 and S4 together, you are getting minus Vs across the load terminal. It is very simple. So what you have to do is, you have to remember these rules, 3 golden rules, and based on that you decide these switching states and you determine what is going to be your load voltage. Now why it is called square wave switching scheme? Because your output voltage waveform looks like a pure square wave. Okay. So what we are doing here, for 50% time we are applying positive voltage, and for the remaining time, which is again 50%, we are applying a negative voltage. Now you remember I discussed some desirable features for a DC to AC converter. So let's try to understand whether this kind of inverter with square wave switching scheme is good enough to serve those desirable features. So first desirable feature, if you remember, that our average output voltage or current was required to be 0. So in this case you see it is going to be 0. So we'll say this desired objective is met. Now next one, V0, is it controllable? V0 or VAB, is it controllable? Answer is no, because you see for a square wave inverter, its RMS value is going to be same as your Vs. This amplitude, whatever it is, your RMS value is going to be this. So with this simple switching scheme, you cannot control output voltage. Then frequency. Output switching frequency, is it controllable? So what is the output switching frequency? This is your time period, Ts, and F is nothing but 1 by Ts, right? So you can control this Ts. You can apply square F for this duration also, right? maybe 1/4 of TS, let's say. So then your frequency will also change accordingly, right? So by changing your switching time period, you can control the switching frequency. So here answer is yes. Then whether I can control the phase, right? So here also again answer is yes, because you can control the time when you are going to turn on a particular switch pair, and that's how when to apply positive voltage, when to apply negative voltage, that you can decide. So if you wish, sometime you can generate this kind of voltage waveform, and you can also generate this kind of voltage waveform which is phase shifted. So that's how you can control this phase amount, right? So this is yes. Then another requirement was we wanted output voltage to be sinusoidal. So are you getting a sinusoidal output voltage? Obviously answer is no, because it is a square wave. It is not at all sinusoidal waveform. And how much harmonics are there in this waveform? How do you determine? You can apply Fourier series and you can determine, because this is a periodical signal, so you can easily determine what are the different harmonic components present in this inverter, which is very important to get some parameter like total harmonic distortion. So this definition you have already studied, and simply you apply Fourier series to this square wave and you can calculate what will be the TSD. So I already gave you the solution. You work on it and determine what will be the TSD. Now this square wave is a very simple waveform, but in other application you may get a very complex kind of waveform, maybe having more number of pulses. Then doing hand calculation is difficult, so you can use some mathematical tool or software like MATLAB, where you can generate the desired waveform that you want to check your TSD value, etc. And then you can feed it to some TSD calculation block or first Fourier transform, this kind of blocks, and you can determine what is the TSD value. And also you will be able to determine if your fundamental amplitude is 100%, with respect to that, what will be your amplitude of other harmonic content. For example, if you want to know the harmonic component of this square wave, you feed it to this kind of frequency analysis tool. You will see that the first component, the major component, will be the fundamental component. Basically, it will having the same frequency of this square wave, so that is going to be a fundamental component. Then you will get third harmonic component, then fifth harmonic component, and all odd order harmonics for a square wave. So if this frequency of this signal is 50 Hz, your fundamental is going to be 50 Hz. Next you are going to get 150 Hz, then 250 Hz, and so on. Okay, so this simply you can analyze through Fourier series or using some mathematical tools like MATLAB or Plex or similar other softwares. Now let us try to understand three very important questions for square wave inverter, and it will help you to understand square wave inverter in better way. So can we obtain sinusoidal voltage using square wave scheme? Directly we cannot obtain, because ultimately we are getting a square wave, right? But there are some way to finally get a sinusoidal voltage across the load terminal. We'll discuss next. Then I keep on mentioning repeatedly that this body diode are required for voltage source inverter, but they may not be required for a very specific cases, so that we need to discuss. But remember, in general, VSI should always have this body diode. Only in a very few cases, under only resistive load condition, you don't need the diode. But in most of the other cases, you will see our loads are mostly inductive in nature, and also we will be using some filter element in between, right? So for that, this diode is absolutely required. We'll discuss more about it. And one more drawback we saw, that the output voltage amplitude is not controllable for square wave inverter. So how you can control the output voltage magnitude, that also we need to study. Now let's try to understand how we can obtain sinusoidal voltage using a square wave switching scheme. What additional thing we can do to achieve this goal of sinusoidal voltage across the load terminal. So square wave switching scheme will give you at the output of inverter a square wave voltage waveform. And if you analyze it in terms of Fourier series, what we saw in the last slide, that it will have fundamental component, let's say 50 Hz if we want. Then next will be third harmonic, which is 150 Hz, then 250 Hz and so on. So we want to retain this one, but we want to eliminate this higher order harmonics. So you must agree that we need to use a low pass filter, because we want to eliminate high frequency component, we want to retain the low frequency component. So we must use a low pass filter whose gain versus frequency curve looks something like this. At the cutoff frequency, it will give around 70.7% gain, and beyond that it will offer lesser gain, so that all higher order harmonics you can eliminate, and below cutoff frequency it will offer decent gain, so that those frequency component can be reproduced at the output. And how do you get a low pass filter? You can use a LC filter, right? That also we discussed in module 1, that if you connect L and C in this particular fashion, you will get a low pass filter. Remember, we don't want to use any resistance in the filter, because resistance will attract more losses, and one of the major goal of power electronic solution is that we want to design an efficient solution. So we don't want to put any resistance unless it is absolutely mandatory. So for filter, resistance is not mandatory. We can design filter using inductor and capacitor, and that's what we are going to do. So this is an inductor and this is a capacitor, and the cutoff frequency of this kind of filter will be 1 by 2 pi ruled LC. So if I know the cutoff frequency, for example, here I would like to select my cutoff frequency in between 50 Hz and 150 Hz, right? So I know roughly what will be my cutoff frequency, and based on that I can decide L and C value. Their product I can decide, but how do I decide L value and C value individually? That also we'll study in a future lecture. So finally, your inverter is giving you output between AB terminal, which is a square wave, and this filter will filter out all higher order harmonics, and finally your load will get fundamental component. So that's how we can still get a AC voltage which is sinusoidal in nature across the load terminal. But main drawback of this approach is that you can see lower this cutoff frequency, higher will be LC value. So here cutoff frequency is, let's say it is 100 Hz. So this LC product has to be higher. That means your filter size will increase. Now if I had a solution that I could eliminate all these lower order harmonics, and my higher order harmonic starts from some high frequency value, let's say 10 kHz. So what I have, fundamental at 50 Hz, next frequency is 10 kHz. I don't have in between any frequency. So then I can decide my cutoff frequency maybe at 9 kHz or maybe at 5 kHz, etc. So then this cutoff frequency will go up, and as a result your LC value requirement will come down, and that's how you can reduce your filter size. So this is one of the drawback of square wave switching scheme, that the filter size requirement is much higher. And in later class we'll study a modulation technique known as sine triangle modulation, sinusoidal pulse width modulation, where you will see that filter size requirement will come down, and that is one of the main motivation of using those kind of switching strategies. Next topic, we need to discuss why diodes are required and whether we need diode under every loading condition. That also we'll study. Now as you understood, for a square wave switching scheme, if I turn on this diagonal pair S1 and S2, I'll get positive voltage. If I turn on S3 and S4, I'll get negative voltage. Now if I have a simple resistive load, pure resistive load, right? So then your current will also be similar to your voltage waveform. It will be just a scaled down version, right? So the current will be nothing but voltage by resistance, right? So for this kind of appliances where you are using just a resistance across this load terminal, then you don't need those body diode. Now let's take a different case, that if it is a pure inductive load. So how your inverter circuit will look like now? You are having a inductive load, and let us assume that all elements in this circuits are ideal, right? And this is your DC source. And also assume that at initial level, your current flowing through this inductor was 0. So I0 was 0 ampere. Before we started giving gate pulse to this inverter, all switches were turned off and inductor current was 0. Now first I will turn on S1 and S2, and voltage across the inductor, it will be VAB, or this one. So as soon as I turn on S1 and S2, voltage appearing across the inductor will be plus VDC or VS. And as you know, inductor voltage equation, VL is L didt and I is VL by L integration dt. Of course, I am assuming this VL equal to VAB equal to VS is a constant number. That's why it came out of integration. And also for the integration, there will be the previous value, right? Initial value you have to add for any integration. So this is how inductor current equation will look like. I is V by L integration dt into I0. So initially when I started, I0 was 0 because there was no initial current, and this is constant number. So your I will be V by L into T, and current will increase linearly. At this point, we are turning on S3 and S4, and as soon as we do that, we are applying a negative voltage of amplitude Vs, let us call it Vs, minus Vs across the inductor. So what will be your inductor current? It will be minus Vs by L T due to integration dt plus I0. Now this I0 is same as this value now. So it is having a negative slope and current will come down to this point 0, and the next cycle again it will start from 0. So your current, you will see it looks like a unidirectional current basically. So current will always flow from this direction. So this is a very important exercise. You should understand each and every point of this discussion in more detail, and it is a very interesting case and very interesting question for Viva also. So we are applying a AC voltage across an inductor, and its current you are seeing it is a kind of a DC, right? It is not going to negative direction. So when S1 and S2 is turned on, current is positive, and how it is flowing? Through this S1 and S2, the current is flowing. And when you have turned on S3 and S4, current was still flowing in this direction, and as you know, inductor won't change its current direction suddenly. So it will like to still flow in the same direction, and it will need those body diode to complete that path. So current will now flow like this. So during this first half cycle, S1 and S2 will conduct, whereas during that negative cycle, actually D3 and D4 need to conduct. Even though you are giving gate pulse, remember we did that revision slide, even though you are giving gate pulse to these switches, actually their diode will conduct. And if you do not provide any diode here, then what will happen is that inductor current has to reverse suddenly, and it will lead to high LDIDT, a large voltage across the inductor, which may destroy your switching devices. So if you are using an inductive load, this kind of diodes are absolutely mandatory. Next case, let us discuss what happens if I connect a capacitive load. So again, let us try to draw the circuit diagram. Again, initially all the switches were turned off, so the voltage appearing across this capacitor is going to be VC at time 0 is 0 volt. Now as soon as you turn on, let's say S1 and S2, what will happen? This Vs will come in parallel to this capacitor C, and this capacitor C has to charge quickly to Vs in no time, and that will require infinite amount of current ideally, and that may destroy your switching devices. So that is the reason that two voltage sources having non-equal magnitude should never be connected in parallel, and that's why this kind of ideal or pure capacitive load we should not use in voltage source inverters. Next case, we can study about RL load, and you can also study RC kind of load or a combination of RLC. All these things you can study as a homework. If you apply a RC load, how the current waveform will look like. If you apply a RLC load, how it will look like. And if we apply RL load, as you know, as you can predict, basically the current waveform will look something like this. You are applying, your voltage waveform is not going to change. Remember, in the first class I discussed that the voltage appearing across the inverter terminal doesn't depend on the load condition. It will be decided by the supply voltage and the switching scheme, whereas current will get decided by the loading condition. So here, as soon as you turn on S1 and S2, you are going to get a positive voltage, and then S3 and S4 you turn on, you are going to get a negative voltage. And it being a RL load, your current waveform will look something like this. You can take up as a homework, and you can derive an expression for this current that you can solve in tutorials. Decide some magnitude for this voltage source, then you apply 50% time when you are applying positive voltage, 50% time you are applying negative voltage, and how your current waveform is going to look like. So what you will see that during positive half cycle, for some time current is actually negative. So you are giving gate pulse to S1 and S2, but actually current is negative. That means current is flowing in this direction, right to left, through the diodes. So through diode D1 and D2, current will flow in that short duration. Depends on RL values, whether it is a short or slightly longer, that you can easily calculate using proper expressions. Then current will become 0, and then current will reverse and it will be in positive direction. Then actually this switch S1 and S2 will conduct. So during positive half cycle, for some time D1 and D2 will conduct, and for some time the switch S1 and S2 will conduct. Similarly, in the negative half cycle, for some time their body diode will conduct, and sometimes those switch S3 and S4 will conduct. So what is the summary? If it is a pure resistive load, there is nothing else at the load terminal, right? Then you don't need the diode. But if it is a inductive load like this pure inductance case or this kind of RL load, then you definitely need this anti-parallel diode, because they need to carry current for some amount of time. Then the next problem was that the output voltage was not controllable, because ultimately we were getting a square wave at the output terminal whose magnitude is fixed, so you cannot control the output voltage. So is there any way by which we can control the output voltage? So one of the strategy is, instead of applying positive voltage for entire half time, so this is my TS by 2 period, and this is TS by 2, right? So entirely it will be TS. So instead of applying a positive voltage for entire TS by 2, you apply it for some duration, and for the remaining duration you apply 0 voltage. Now how do you apply positive voltage? You turn on S1 and S2. And how do you apply 0 voltage? You turn on S1, S3 or S2 and S4. So this way I will be able to control what will be the RMS value at the load terminal. And sometimes you would, instead of applying a long pulse, you can apply a train of pulses, right? For example, if you are applying this kind of long pulse to an induction motor or similar load where it is having inductance as a parameter in the load, then there may be a chance that your current will build up and it can exceed some value where inductor may get saturated. So there you would like to apply train of pulses. So current will build up, then it will decay down, again it will build up, decay down, right? Those kind of situation will happen. It will prevent it from getting saturated. So instead of applying a long pulse, you break the pulse in small pulses and apply it to the load. So this is also possible. And in both of this, you will be able to control the output voltage by deciding the width of the pulse. And how do you implement this kind of situation? That we are going to discuss in the next slide. But you will agree that this waveforms doesn't look like sinusoidal waveform. And again, you can apply some tools like Fourier series and you can determine what is the harmonic content of this kind of waveform, then what is the THD value, etc. And how do you finally implement this kind of strategy? You can follow this figure. For a single pulse modulation technique, for multi-pulse modulation technique, you can follow this. These are self-explanatory, so you just go through them and you will understand. This is the last part of this lecture. What are the advantages and disadvantages of voltage source inverter? So as you understood, voltage source inverter is very easy to implement, right? You turn on for the half time, you turn off for the half time. It is very easy to control and very simple. So that is the main advantage of this kind of converter, but it has several drawbacks. As you understood, the output voltage is not controllable for a pure square wave inverter case. Then it is not at all sinusoidal. It has quite high THD. So how do you solve this problem? That we are going to study in the next class, where we will learn a concept called sine triangle modulation, where we will learn concept like unipolar pulse width modulation, bipolar pulse width modulation, etc. so that we can make our output voltage more closer to a sinusoidal waveform, and we shall also be able to control the output voltage amplitude. Hope you have understood the concept that are discussed in today's class, and if you want to study them in more detail, you can follow these references. Thank you for attending this class.